This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I don't have any handouts for you today. You should pretty much be done with all the handouts. Yesterday's section solution hasn't been posted on the web yet, but Ryan will do that now. And, the next time you're going to see me will be Monday morning at 8:30 or Monday afternoon at 3:30. Remember, you can take the final at either time. You don't have to tell me ahead of time which time you're planning on taking it. You can only take it once. I will post the exam as a handout at 3:30 that afternoon. So SCPD students who are watching me right now, just plan on downloading it. I'm a little bit more flexible on when you take the exam because I know you work, but I need the exam faxed back from you, faxed in by Tuesday at 5 because we're going to crank on grading that Tuesday night. Okay. You have an assignment due tomorrow night. You can use as many late days as you want to. I mean, it was designed so that you weren't supposed to use 5 late days on it. But if you have 5 late days and you want to consume them and hand it in after the final exam, it's not a problem because we're not going to be able to grade that until after the final anyway. You should definitely if you haven't gotten assignment 4 back yet, then let me know because you should have gotten those back. I've seen all the grades fly through my email. Assignment 6 is being graded right now. I told my TAs they have to have that back. That's a seashell. They have to have the assignment 6 back to you by the weekend so you can make sure that you understand threading to the extent that I'm going to test it. Assignment 7, I actually don't think you're going to get back by the final, but that was the scheme assignment. Historically, if there are 200 of you in the class, 195 of you get A's or A minuses on that because you all get it working and it's this new language, so we actually have, I don't want to say we have low standards, but we just don't press you on style that much. If you got that working, you're probably fine, so you're not going to be surprised by anything in terms of your feedback on that assignment. Okay, so I left you with enough Python to get the assignment done. What I did is I invited a coworker of mine from Facebook who is responsible for that noise. I invited a coworker of mine. He's actually kind of my boss for the first 6 or 7 weeks of the time I was there. And he is a programming language enthusiast as well. He knows 2 languages called Haskell and ML that I don't know as much about, and I asked him to speak about one of them called Haskell. So I'm just going to hand it over to him and let him kind of present a language to you that you would not have otherwise seen had I been the only one teaching the class. Okay, so let us do a little bit of a microphone switch right here. This is Sasha Rush, and I will do this. And I'll let him talk.
Okay, so I'm going to talk today about Haskell, which is kind of like an avant-garde programming language. It's not something you'll see in like a lot of companies using these days. If you want to like get a job, you should be like a really good C programmer. If you want to like program like the future, you should like learn a lot of Haskell. Think of it as like the Schoenberg of programming languages. So here's a little history of Haskell. It comes from the same family as like Lisp and Scheme. It's a functional language, which means setting variables is discouraged. Using functions all the time for everything is really how you get stuff done. There's things like map that you'll be used to from Scheme, but there's like a million less parentheses, so that's really good. Then that kind of went down to these languages called ML, and there's a language called OCaml, which is like a modern version of ML that's pretty popular. These languages took Scheme and kind of merged it with C in an interesting way, in that they're statically typed. So you have like integers that are actually integers, and if you try to like use an integer with a string, it'll fail. That's really nice because you add a lot of like speed to the program, but it's really annoying in like C because you have to type integer everywhere. So the kind of brilliant idea behind ML is you write code that looks like Python code, but it figures out the types for you, and so it'll throw an error, but you don't have to put any of the definitions down. It's like pretty amazing that this like brilliant idea that was invented like 30 years ago isn't used today, but I think more and more it'll become like pretty standard. Latest version of like C# and future versions of JavaScript will possibly have this kind of stuff in them. So then this language came out called Miranda, which was like a proprietary language. But it had this really neat idea that we'll talk about a little bit later, which is that it had this thing called lazy evaluation. And lazy evaluation you won't see in pretty much any language but Haskell. The reason of that is because all the researchers working on this problem got together and they said, hey, let's make kind of an open source version of Miranda that's lazy and is standard, and we can like all work on together. So it's a really good thing if you want researchers to like look at your language, don't make it proprietary. This all came together in Haskell 98, which, as per the name, came out in 2003. That's kind of like the current kind of modern version of Haskell. Since it came out in 2003, it's been like incredibly popular with like a small group of like pretty dedicated people, and they've been kind of working on it pretty hardcore for the last 5 years, and it's getting to the point now where it's like really good. Okay, so Haskell's pretty neat. So it's safe like Java. So when I say safe, I mean it's really hard to make a program that compiles and then fails. So this is like really annoying about a language like Python, is that you're constantly running your programs, they're constantly failing, you're constantly writing them again. It's really nice, particularly for applications that matter, things that like aren't websites, that the program that you compile, you know it's not going to fail for like a dumb reason that you like left something in. So what does this mean? Well, this means that if you try to like add a string and like an integer, it's going to like fail. The little colon syntax is kind of like the cons operator in Scheme. It means like put this at the start of a list. So if you try to put a string in a list with numbers, it's also going to fail. So this again is different than Scheme because Scheme is not statically typed. Scheme will let you put kind of anything in a list. In Haskell, if you have a list, it has to all be the same kind of type of thing. Okay, so it's like Java, but safer. There are a lot of kind of funny issues in Java. Here's one of them. So I have an object called temp, and I set it to null, and then I try to run this method that I like know should be on object. Like it's been guaranteed for me to be on object, but it can fail because temp was null. So like this is like a pretty common thing that most people are used to in object-oriented languages, but it's like this huge issue. Like there's all these possible runtime errors that like you're not protecting for. Here's another one. So we had this guy named named temp that was an object, and I'm trying to cast it to become a string, which is okay in Java. You're allowed to, I think it's called downcast. You're allowed to move from one guy to its like child. And it has this huge possibility of failing, because in this case, it's not a string. You can't pretend it's a string. Okay, it's expressive like Scheme, so like I said before. So you have this like map function. The kind of square brackets are a list. It's kind of a list literal. It's similar to list literals in Python. And you can run kind of anonymous functions over it. So this function maps adding 1 to a list, and you get back a list with all the numbers plus 1. Here's another example. This is a sort by function. Sort by takes a comparison function and does a sort with that function. So this one here just sorts a list by the standard ordering. Okay, it's fast like C. It's not as fast as C, but like it's getting there. It's kind of like on the like the order of magnitude. And here are like some stats. This is like not the way to think about speed of languages, but it gives us like an easy way to look at it. So this is from like the computer language benchmark game online. Just to give you an idea, the big difference is that types not only guarantee like safety, they also allow you to make a language pretty fast. You know when you see a plus sign that you're going to be adding like 2 integers and not going to have to check for this failure case. And that makes the language like a lot faster. Okay, most importantly, it's pretty fun. When I say fun, I mean like if you want to like do a multiplication function, you just do a multiplication function. You don't have to like write all the other stuff around there. You can do things like mixed arrays. This is kind of like the tuple syntax in Python. I don't know if you've seen that in this class. And finally, it's got a lot of these like crazy things that you can kind of just throw in. Jerry said that you guys saw very briefly list comprehensions in Python. So list comprehensions were an idea taken from Haskell. This is the syntax for taking all the numbers from 1 to 10, multiplying by a 2, and giving that back as a list. So this guy on the right here is kind of like range in Python, and the whole thing is like a map. OK, so I should say now that I'm going to show a lot of code examples as we go through Haskell. So feel free to like interrupt me at like any time and ask questions. I wasn't really exactly sure what level I should be doing this at, so some of this may be like a little bit crazy. OK, so we're going to look at Fibonacci, which is like pretty standard, I guess, programming example. So for you guys who don't remember, the Fibonacci sequence is simply a sequence where you take the last two numbers, you add them together, and you keep on going and going and going and going. So this is the kind of definition. OK, so here's the Fibonacci sequence in Java. So we have a function fib. We give it an n, which is how long we want the sequence to be. It returns a list of integers. Java is really nice. It has this new generic syntax that lets you say what the list is of. So the first thing we do is we declare the list. That's our sequence right there. We set the first value. We set the second value. And we do a for loop. It's pretty simple. It kind of describes the program that we're doing step by step. Each line says what it's doing, does something, moves on to the next line. So like, I think that's pretty good. So this is it in Haskell. So like, where did it all go? Like, where's all the coding, right? Where's all the writing? So in Haskell, like, we take a different approach. We like go back to the definition of what this thing was, and we like just write it. Okay? We're not concerned with how the machine represents it. We're not concerned with like the ordering, how it's presented to the user. We're just concerned with like what's the math, like what's going on here. And you can kind of describe it in the most like basic of ways. And so I told you that this is safe. I told you that this is fast. So you can see that it's fun, but like the other two, it's hard to describe what's actually going on here that makes this work. So let's like dive down into the details. OK, so here are the two like bodies of these functions. So let's try to map like each part to each part. So I said before that the colon means like a list operator. It means like, hey, put this at the start of the list. So we can see that we started off with 1 at our list. So that maps down to, hey, the sequence of 0 is equal to 1. And then we can see the second part is equal to 1. So that part I think makes sense. The part I'm going to have to sell you on is what this last guy does. So what's going on here? So one thing you can see is that we're using the word fib within that expression. And we're also setting fib. So it seems really weird that you can use the variable that you're setting within the variable itself. So that's a little bit strange to get over. So the reason this works is that we want to think of this not like a variable, but like, almost like a function. So it's like a recursive function, which you've probably seen before. So if we think of fib as a function, it makes a little bit more sense. We're taking like the old value of fib and putting it in the use of fib. What does tail mean? Tail is similar to, I guess, it's Kadur in Scheme or tail in Scheme. Yes, CDR. It means like take the end of a list, not the first element. And then what is this zipwith doing? Zipwith is kind of like the map function. It says, hey, map this function over this list. Except instead of just mapping the function over one list, it takes two lists and combines them with the function. Okay? So we take the two lists, we combine them, we're good. So let's look at this in more detail. So first off, how can we use fib as a variable? Well, what do we know about fib? We know that fib starts with 1, 1. It's a list that starts with those two values. And then after 1, 1, it's a question mark. We don't know anything about what's going on after that. Okay? What do we know about tail fib? Well, we know it starts with 1, and then we don't know anything about it, right? It's the same blankness that we saw before. So then the question is, what is this zip with guy? So as I said before, it's going to add these two guys together. So we know we have 1, 1, and we know we have the tail. So we zip them together, and we get 2. Once we know that's 2, that goes to the end of the other two lists. So we have it there. We then add them together again. We get 3. And we keep on going. So what happened there? So the trick is that Haskell is what's called a lazily evaluated language. And that means it'll do no work at all until it has to. It's like the undergrad of languages. So we start with 1, 1, and then we get to like zip with. It's all in what's this like block. It's like in a jail. It's called like a thunk. This is something that's there that we have to evaluate that we haven't evaluated yet. So then I say, hey, I want to take the first 5 values of this guy, and I want to get them out. So then what happens is the first 5 values get kind of like pushed through. They get converted from like thunk land to like real values. And then we just leave the rest. We just say, hey, we're going to evaluate that sometime in the future. And that's pretty cool. It's cool in that it means we can kind of have infinite lists. These lists can go on forever, and it's like totally cool in your program that the list is there because you're not going to spend infinite time evaluating the entire list all the way through. A good comparison like this is the xrange function in Python. So instead of actually constructing the range of the entire list, it simply just takes one value at a time as you request them. So it's kind of like that, except for everything. Like that's the default standard. So here's a good example. Actually, let's skip this guy. One thing that's kind of frustrating about programming languages is if you want to have a function that kind of works like the if statement does, it's really hard to write it. So imagine we have a function in Python called myIf, and you take 3 values, the like Boolean value of like which branch to go to, and then the if branch and the else branch. Then if the first guy is true, we take, oh, sorry, this is a typo. If the first guy is true, we take the B branch. If the second guy is true, the first guy is false, we take the C branch. Sorry, totally out there. So why can't we do this in Python? Anyone have any ideas? So what happens if the B value is like print hello? So like if you have any kind of like effects in either your then branch or your else branch, like print, for instance, or like, I don't know, make like an internet request, then you have this problem where if that branch doesn't get called, that value still goes out on the screen. Okay? So if you say like if true, print hello, if false, print goodbye, right? You're going to get hello goodbye because both those like statements are going to get evaluated before they're sent to the function, and then the function is going to just return their result. Okay? So in a language that's lazy, nothing gets evaluated. It just remains in its thunk until it's needed. And then when it's needed, it gets evaluated. So the branch that failed will just go away. Any questions with that? Or? Okay. So then the second question is, well, how can it be fast? I said before that to be like fast, you really need to know the types of what's going on. And if you looked at our old guy, we didn't like write any types at all. There are like no types. There's no ints. There's no There's no functions, there's no lists, there's no anything. So the trick is that Haskell, it kind of like figures out the types. So I'm not going to go into this too much. There's like a whole body of study on how to do this correctly. But we can kind of just play with it. So what types do we know to begin with in this function? Anyone? What values here have types? Yeah, the 1. We know these guys are both ints. OK. And what's the type of fib? What did I tell you about lists that we know about the type of fib? What's that?
Homogeneous.
Homogeneous, right? OK. So if the ints are both there, OK, I'll stop asking questions. But if the ints are both, if we know these are both ints and we know they're in a list, that means we know that fib must be a list of ints, right? Offhand, even to start with. OK. So if fib's a list of ints, it means this last guy has to be a list of ints or we'll fail. OK, so let's check that it is. Well, we know that fib is a list of ints because we just said so. And we know that tail fib also must be a list of ints because it's just the tail of a list of ints. And we know that zip takes two lists and adds them together. So therefore, it's also going to be a list of ints. So that means the whole thing type checks, and we're good. So the compiler knows what the types are. It can make it faster. We know that we didn't make a mistake, so it's safe, and everyone's happy. OK, cool. So now let's go kind of more deeply into what the types are within Haskell and look at them. OK, so we're going to start off with a bunch of basic types. We're going to have an integer type. We're going to have a float type. We're going to have a character type. OK, and like scheme, functions themselves are also going to be a type. So we can pass functions around in that way. So the way we look at types of functions is with this kind of double colon notation. Think of the double colon notation like a declaration in like Java. It just says like, this is what the function is. So what does it say? Well, we have a function called add1. It takes a number, and it adds 1 to that number. You don't need to use the word return at all in Haskell. So the result it's returning is the number plus 1. So the way we write it is we write int arrow int. That means we take an int, we return an int. OK, how do we do adding of two numbers? You write the word add. You write the arguments as like spaces after the function. So it's add val1, val2, and we just add those guys together. Now this guy's a little bit confusing. The way you write the type signatures when you have two arguments is arg1, arg2, return value. OK? So that's just how we write functions. OK, so there's another kind of type. And this is like a type the user defines. So in Haskell, you're allowed to define your own types and kind of just put them into the system. Here's a data type for Boolean. So a Boolean type can be either true or it can be false. OK, we put that guy in there. It's now a type in the system. We can write the word true, it means something. We can write the word false, it means something. Here's how character is represented. Character is just an or with all the different letters possible. Here's color. So color could just be like red, green, blue, whatever. You can kind of write any of these that you want. Just like anything you make up, you can just put into the language itself. OK, so now we're going to look at how you do a function over this type. So this is the not function. It takes a bool, produces a bool. Bool is this new type we just added to the land. So here's the function. So takes the val1. If the val1 is equal to true, so we're now using our type, true. Then we're going to return false. Else we're going to return true. OK? Pretty simple. These are just new things we've added to the language. It's even cooler is that you can use your types in a kind of different way, which is called pattern matching. The way pattern matching works is instead of doing before, I can write the same exact thing, the same thing we just wrote, as this. So this means the not function, when given the pattern true, will return false. When given the pattern false, will return true. So I've like matched on the type that I want, and I have a specific value for that type. Yeah?
When you define a function, do you always need to both give the type information, like the bool, arrow bool, and also the definition?
You don't actually have to do it. It will like figure it out for itself. It's kind of used as documentation though. So it's like a good way of just telling other people who read your code, this is what the function does itself. Also, people write them sometimes because sometimes Haskell will figure out the type, but it'll be like very generic. So it'll kind of generalize your functions for you. And sometimes that can be a little bit confusing when you get error messages and things like that. So it's often good practice to kind of put that there. OK, so let's look at pattern matching a little bit more in depth. Here's the AND function. This is kind of like the Boolean combinator AND. It takes a bool, takes another bool, and produces a bool. So if one's true and one's false, it returns false. If one's false and one's false, it returns false. If one's false and one's true, it returns false. And if one's true and one's true, it returns false. OK? OK, so if you've programmed in C and newer versions of Java, you may be familiar with this concept of an enum. An enum is often used in a similar way if you want to do like true, false, or colors or something like that, where each one of these statements is assigned an integer value. So false may be assigned the value 0, and true may be assigned the value 1. That's fine, but it's pretty much like a huge hack. Like, it's really confusing because some things may like, you can like add different kinds of enums and things like that. So just to show you that these are not the same thing. So here's our apple type. Here's our orange type. And if we try to like take two values of these guys and compare them, it's going to fail. It's going to say, hey, these are not the same type. Just like when you tried to add a string to an integer, not allowed, that's a fail, we're done. OK, so now we're going to talk a little bit more about user types. So the other thing that's kind of cool about these types is that you can parameterize them with other values. Yeah, oh, I'm sorry. So here's the orange type. So now we have like this other orange. And well, so first of all, we have seeds. And seeds has two values. You can be like seeded, or you can be seedless. So again, similar to like just true, false. And then we have orange, which looks the same as before, except we have this other guy that has a kind of space and another type put into it. So you can think of that guy as like an argument to the first type. So it's just like when you use this in practice, you can say, hey, I have my orange, and my orange is a navel orange with seeds. Or it's a navel orange without seeds. You can kind of put arbitrary other types as like arguments to the types originally. So this is kind of similar to like a constructor in an object-oriented language, where you kind of just like, when you make a new instance of that object, you can kind of pass in arguments that kind of are properties on the object. OK, so I said before that in Java, any object can be the null, just null, like stop by. So I kind of disparaged that before because it can be really dangerous. If you like don't know an object's going to be null, it's kind of bad and you can like cause failures. It's also really useful in some cases because like sometimes things just fail and you want a null coming back as kind of a marker that said, hey, this guy doesn't exist, it can't exist, it was a failure. So we can represent this guy in Haskell too. So here's with string. So we're going to add a new type to our language called string stuff. And it can have two values. So the first value is it can be null. And the other value is it can have some stuff in it. And that some stuff contains the string that it's supposed to be. Okay? So it's just like a string in Java in that it can anytime be null or be some value. And it has that value contained within the type. So like this is pretty good. It'll like work for strings. But like let's say that I have some new data type like oranges. And I want oranges also to possibly be null or have some content in them that we want to look at. The problem is this guy only works for strings. So I'm going to have to write an orange stuff too that looks pretty much exactly the same, but works for oranges. So what we really want to do is parameterize this definition here, not only with this value, which is the like argument it takes, but also with the type of that argument, so that we can maintain our type safety without breaking things. So this is kind of like list in Java. So instead, now we're going to have like a data type called stuff. So now I have this argument on the left side too, which is like the type of the sum guy. So it's like an argument, just like an argument to a function, but an argument to like a type definition. And we can kind of carry that argument through. So now if I want a string, I say it's of type stuff string, and then the sum can contain a string element, and so forth. Yeah?
If you have both string and are the possibility of null, what type of null?
So are you talking about in
The previous.
this null?
Yeah.
So the type of null would still be str stuff. So like, let's see. So null, since it's defined in this data, str stuff, its type is str stuff.
So it would be reserved for str stuff.
Oh, yeah, sorry. You can't actually use it in both. Yeah, definitely. Yeah, if I tried to type in both these definitions, it would just like fail. And this works with any type A. Okay, so here's an example. So we're going to try to do division, but we're going to make it safe so that if you try to divide by 0, we fail. So if you divide by 0, we return null. Oh, sorry, this shouldn't say object, it should say stuff. And when we try to divide by a regular value, we return sum and then that value itself. Okay. Why can't we just do this guy for the second part? So like, why do we have to have this word sum there? What's that?
So it knows what null is? Or is that typing it right there?
Yeah, well, so we definitely know the null one. But what would happen if we did this bottom guy? Why would it fail?
It would be returning a different type than the first guy.
Yeah, exactly. It would be returning an int type, not like a stuff int type, which is the difference. Cool. Okay, so let's go on to some more kind of cool types. So now let's do a list type. So a list type is similarly typed to what you've seen in Scheme. It has kind of a pair, like a cons to start with, and then it has like an n value when you get to the end. And this is often abbreviated, as we showed earlier in the talk, as the colon operator. So we say that a list is some value and then the list of that value. And when you get to the end, you have kind of like a blank, like a stop type. Okay? This guy's a little bit crazier than what we've seen before because it's what's called a recursive type definition. You'll notice that I'm using the same definition I used in the data side on the actual definition. And that just lets us say, like, hey, this value contains another value with inside of it. So like a list, when you do the tail operator, contains another list right there. Okay, so here are some examples. The string, the type string defined in Haskell is just a list of chars. So everything is still just consistent with this type definition we showed before. So yeah, so now why does this fail? Why do we have to have homogeneous lists?
So it's fast.
Well, I know why we do it, but just because it's fast doesn't mean we should like prevent people just because. So like let's look at this definition. So what was that type of that thing we just showed? So this guy is type list char because they're all characters. The guy at the top is of type list int because they're all integers. And so when we try to do this guy, we have integers and characters kind of intermingled in the type definition. And so if we look back at this guy, well, we said a list starts with a type. So if this guy is type int, it means it can only have type int inside of it, right? So if we try to put strings inside it or chars inside, those two aren't going to match. That definition is going to fail, and the compiler is going to throw an error. Okay? So there's nothing special here, nothing like magic, like keeping the list consistent. It's just based on what the type of the list is.
Is there a way to have it homogeneous?
So there are kind of ways to do it, but you lose again like speed and like safety. We'll show you one a little bit later that's like one possible way of going about it, but it's kind of like an open question of how to do that well. Okay, so let's look at some kind of functions over these kind of objects. Okay, so here's like sum. So what sum does is it takes a list of integers and it returns just an integer. So again, we're doing pattern matching just like we did before with true and false. But here the pattern is, hey, is this a blank list? If it's a blank list, we return 0. And then the other thing we're pattern matching on is just like we did before. It's pattern matching an int and a list of ints right in the function definition. Okay? And we take those values. So we have a value next and a value rest. And we can kind of act on them just like their values. So all we're doing here is adding next to the recursive sum of the rest of the list. Okay, here's the next guy. This is map. You'll probably have seen this definition before from Scheme. So what is map? So this is the first time we've seen a function used as a type within another function. So as I said before, the way we read this guy is map is a function that takes a function from some type A to some type B. Then it takes a list A and it returns a list B. Okay? So a map over an int list would take a function from ints to ints, take a list of ints, and return a list of ints. Okay? So what do we do? Well, if the list is blank, we do nothing. If the list has some elements, we just apply the function to the first element, and then we put it at the start of another list that's the rest of the elements with that function applied to it. Yeah.
If you had, on any of these, if you had the empty list below the main function, would it compile?
Yeah, it would compile. You'd actually be totally fine in these cases because these two are different types. So think of the first one like true and the second one like false. So you can have them in any order because it's just matching is this type, that kind. Yeah. I guess I should say one other thing, which is that you can also write map fun and just give a variable. So if this said map fun list or ls or something, then it wouldn't work to switch the two, because the first one would match an empty list also. Does that make sense? So it matches the most general possible one. Okay. Oh man. So this is my. Let's see if we can get some audience participation for this one. So here are some types that are like a little bit more crazy. So if you guys can I think this is pretty interesting. If you can look at them and just take a guess of what this actually is. Like, what are we trying to describe here with this type? I think we have plenty of time, so we can probably go through these. Okay, so it can be two things. The second thing's pretty boring. The second thing looks just like our sum from before, right? It's just like it has one value in it, right? So what's going on with the first thing? The first guy's a little bit crazy. It can have one value, and then it can have, do you want to guess there? It's a binary tree, right? So the first guy is like a branch, and it has like the two different paths you can go down. And the second guy is like a leaf, which is just the value itself. So it's pretty neat. Okay, so let's look at this guy. One of the things that's kind of cool about type definitions is that a lot of times you can just look at them and say, oh, I know what that does, just from the type definition. That's why I said before they're used by as documentation. They're also how people search for new functions on the web. They're like, hey, is there a function that does this? Let me type in the type definition. So what does this guy do? Well, it takes a function that takes an A and a B and produces a C. Then it takes a list of A's and a list of B's and produces a list of C's. So the hint is we saw this guy earlier. Yeah, this is zip width. This just takes the function, applies it to the two lists one at a time, and produces the final list. Okay, one more. So this last guy, yeah. Well. So this guy looks very similar to a definition we saw earlier, which is of a list itself, which is like a pair and then an end, except that it's got this craziness where it has two variables it's taking to start with. Okay, so we're used to just seeing a list parameterized by one type. This guy's parameterized by two types. And you see this craziness where it flips the types when it goes to cons. So this guy's a list where the types alternate. So the first one, if you give it an int and a string, the first would be an int, then a string, int, string, kind of alternate as it goes. Yeah?
What's the capital A?
Capital A was just me hiding what that would be. So in real practice, you'd give that a descriptive name, like cons or something. Okay, so here's kind of just how we would actually write these guys in practice. The first is the binary tree. The second is the function zipwidth. And the last is this kind of switch list guy, which isn't actually practical for anything, but is a good way to understand how lists with mixed elements would work. Okay, so you've probably learned that object-oriented code is pretty good, and we want to use it. So in Haskell, there isn't really any object-oriented stuff at all. Part of the reason of this is that functional programmers hate object-oriented code because they think it's just functional code in disguise. So there's a whole history of those two movements. The more practical reason is that it would be kind of hard to use it in Haskell. For instance, because you can't change any values, you don't have variables in the same way. it's kind of useless because there aren't any setters. You can't like change an object's value. And because it's all garbage collected, there's no like such thing as a destructor. So all that stuff doesn't exist. So some of the benefits of object-oriented just like aren't apparent. But there's some stuff about object-oriented that's really good. So let's kind of try to map these concepts back to what you're used to seeing. So the main idea of a class in Haskell is this data type. So you make a data type for everything that you want that you would make a class for. So those two are kind of similar. And then you can think of the actual use of the data types, like the use of true, or the construction of a class, of a list, as kind of like being an object. So it's an object of that class, and you can do stuff with it. And then finally, we're going to look at this thing called type classes, which is kind of poorly named. But these things kind of act like interfaces in kind of a magic way. OK, so here's an interface in Java. I forgot a bool it looks like. But the idea is that like anything that implements this interface must have a function called equals and a function called not equals. And then, a method called equals and not equals. And then we can always call those methods on any objects of that type. So Haskell has a similar idea called a type class. So you make a class, and you say, hey, this is a class called EQ, and it applies to a type A. And if this class exists, that type A, there must exist these two functions. One function is an equals function that takes a type A, another type A, and returns a bool. And one is this not equals function, which takes type A, and returns a type bool. The kind of cool thing that you can do in type classes that you can't really do in interface is actually like implement one in terms of the other. So the default implementation of not equals is simply the not operator applied to equals. So now here's like an implementation of that. So we say the instance of the equals class for the type bool that we defined earlier means that if they're both true, then that returns true. If they're both false, then that returns true. And if they disagree, if they're anything else, then we return false. Okay? And what does this mean? Well, this means that anywhere in your program, anywhere you want, we can now use equals equals on Boolean guys, and it like will just work. It will just like magically work. So here's another example that's like a little bit more interesting. So we defined this stuff class earlier, and what we can do is we can say that, hey, if you have a type that already has an equals, we've already defined the class equals for it, like Boolean, and you have a stuff of that guy, then stuff is automatically defined with equals too by this definition. You can kind of do this for anything. You can say two trees are equal if this definition holds. You can say like two whatevers are equals. Equals like a pretty small example, but what's neat is that there are these kind of general type classes that work over like lots of things. For instance, a lot of objects in Haskell, the map operator will work for them too. So you can kind of imagine a map operator that works on trees, that goes through each element, applies a function, and produces a new tree with those elements in it. And things start to get really powerful when you can kind of define this arbitrary operator, have it work. You don't even have to know what's being passed in, because you know as long as it defines map, your function will work on it. OK, so I think that's about it for my like actual technical definitions. I said earlier, though, that you can't get a job with Haskell. And that kind of made me sad, because I know everyone wants a job. So I thought it would be good to kind of like go through like a couple of like the interview questions that like we give to people and like show them how it would be done in Haskell. I found that people come in and they try to write interview stuff in like C, and they get so confused over like, hey, did I forget this number here, or like, should this be less than or less than equal? And like, it's just like, it's pretty bad. So I think one of the things that Haskell does is it treats you to like think about the problem from kind of mathematical definition and not get worried over like the details of the implementation. So, how to get a job with Haskell. Okay, so here's a common interview question. I figured I'd ask a couple from Google and a couple from Facebook, so that way we're equally screwed if you guys try to come into interview. So this one is like, you're given two lists of sorted numbers, produce like a sorted list of all the numbers. So it's kind of like merging the two guys together. So the problem here is actually not really much of a problem at all. It becomes tricky when you do it in a language where you have to kind of create a new array that has like the size of both of them, kind of like fill them in one at a time, and then like return that array. In Haskell though, it's just a matter of taking both arrays, seeing which element of the two at the beginning is less, merging that into a new array, and kind of continuing to go along. So let's look at the code. So the first thing, as I said before, you always do is write down your definition of what's going on here. So we have a list of integers, another list of integers, and we're producing the merged list of integers between them. Okay, so here's the code. So if both lists are blank, we want to return blank. That makes sense, right? Nothing to do here. If one list is blank and the other guy still has values, well, you definitely just want that guy, because he still has values left, the other guy doesn't, and vice versa. So that's the first three lines. They're just boilerplate. We're just putting them in to do stuff. Now, the actual interesting part is the last case where we're actually doing the merge. So you'll notice here that we can take the head of both lists right in the function definition. We say, hey, if A is less than B, well, then we want to put A at the front of our list, and the rest is just, hey, merge these other two lists that we created, that we had already. That's that guy there. And then, hey, if B is less, then we take B, that guy starts the list, and then we take the rest of them and just merge them together. There's not really any magic going on here. We're not using any like laziness. We're not really even using our type inference. But it's fast. It's like simple. And there we go. So they're just variables. We could call them whatever. It just means the tail of the list. So A is the head of the list, and AS is like the tail of the list. Yeah?
Do the interviewers care which language the interviewees choose?
Only if they're jerks. Yeah?
So is the less than sign the only thing in there that actually forces it to infer that they're int lists as opposed to just generic lists?
Yeah, and in fact, if we hadn't given this type definition in there, what would it infer?
We would have to just rely on tunneling using the less than sign.
Well, yeah, just using less than sign. So in actual practice, we showed the EQ type class. We'd also have a comp type class. The comp type class would have less than, greater than, all those in there. So it would infer that the type would have to be something that has an instance of the comp class. So anything that had that. Okay, so here's another one. So this is the function a2i. This one's a little bit trickier. So what is it? Well, it's a string, which, as we said before, is just a list of chars. And we're mapping it to an int. This means convert an ASCII string to an integer. Okay? So here's the code. So again, 4 lines, so not that long. The first thing we have to do is define this helper function, which we're calling d2i, which means like convert a digit to an integer. The common trick for doing this in C is simply to minus by the 0 character. Does that make sense? Since ASCII characters are in order, you can just minus by 0, gets back the digit. Anyone know why we can't do that in Haskell? I mean, characters are just represented by numbers, right? We should be able to just do that, right? Well, again, as we said before, since there's type safety, we want to distinguish characters from numbers. So in case you accidentally like add them together by mistake, it's like bad news. So we have this function ord, which tells us what the ASCII value is, and we apply that and do the subtraction. Okay. Then this guy's really like the brunt of what we're doing. There's a little trick here called an accumulator. I don't know if you've seen that in Scheme. It's like a way to write recursive functions. when you want it like it's kind of like a more powerful way to write recursive functions. So what are we actually doing? Well, for each character, we're multiplying the previous stuff that we've seen by 10, and we're just adding on what that digit conversion was. So we go through, so if our number is like 1, 2, 3, we first get the digit 1, then we multiply that by 10, we get the digit 2, we add that on, multiply it by 10, get digit 3, add it on, and then we're good. Okay, we're running out of time. I have one more example, and then I guess you want to finish up? Okay, so here's a function to check if a string is like a prefix of another string. So the type definition is list of chars to a bool. Okay, so what are we going to do? Well, we're assuming our first guy is the prefix, and the second guy is the string we're testing against. So each time we just pull off the first character. If the character is the same, if they're equal, then we keep on going. We do the rest of the list. If they're not equal, we failed, because it's definitely not a prefix. So we return false. Then we just handle the two other cases. The cases are, hey, your prefix is blank. Well, that means we got to the end. So if we got to the end, then it's definitely a prefix. That's true. The other case is that the string we're testing against is false, is blank. And that means like the prefix was longer than original string. So like it's bad news. That's false. So that one's 3 lines. It's pretty simple. Cool. So anyway, I hope that this at least like opened your mind to like there being really interesting other languages out there. Haskell's pretty cool because it's both like a research language and it's becoming more and more a practical language. There's like a really great wiki, haskell.org. It'll teach you all kinds of other crazy like magic in Haskell. The particularly big one is I haven't shown you how to like print yet. And as I hinted at earlier, it's kind of like difficult to print when it's lazy. So there's kind of like really cool tricks for that. There are a bunch of different implementations. GHC is the main one. You can download that for like your Mac or whatever. And there's a bunch of like big programs being developed in Haskell like right now. So anyway, thanks for having me. It was really fun.
That is all. I will see you all Monday morning. Don't freak about the exam. I'm not saying it's going to be easy, but it won't kill you either. So, okay, so I'll see you all then. Good luck with your dead week and all your finals. Bye-bye.